Hi everybody. Today I would like to give you my kind of view on signal propagation on a PCB tray. So I've seen this topic a few times, and I think they're very nice explanations, they're very nice videos on explaining this, but sometimes they lack a little bit of the theory behind it. And many times the field animation actually are shown in frequency domain because people tend to use like a finite element method which calculates in frequency domain. So they show a steady state behavior of the pulse on a signal trace and not the real time domain. And this is why I chosen the time domain solver inside GSD Microwave Studio to visualize these fields really in time domain for you. So what we have is a PCB down here with some meander line. The PCB is around 30 centimeters long. The signal width is 2 millimeters and the thickness is 1 millimeter, so it's a 50 ohm trace. And I drive it at that position with a voltage signal. It's terminated with 50 ohm, and you can see I choose a signal like here, so that's the red line. We have 0.5 nanosecond of rise time. The signal amplitude is 1 volt. Then we have two nanoseconds of hold time and zero point 0.5 nanoseconds again as a fall time. So if we look at what is happening actually with the fields, so at the port 1 you can see I choose a so-called edge port which drives a voltage in between these 2 points. So let's go to the electric field. Of course, the voltage is related to the electric field. We are at point 0 in time, so there is no field now. Now I can move through the time, and you can see it's 0.1 nanosecond. You see the pulse appearing, and of course, the electric field is not only bound in there. The electric field, of course, appears in the whole domain. Of course, the max values of the electric field are between the signal trace and the ground plane. But of course, the field has a certain extent. So if we look at the field here, of course, if we get close down here to the signal trace, it's looking like I would expect to if we set it to 1000 volts per meter, because we apply 1 volt between signal trace and the ground plane, which is a 1 millimeter distance. So we expect the electric field to be 1000 volt per meter. It's not yet that value because we are at 0.2 nanoseconds, so only at 0.6. This is where the signal is fully applied, and you can see that creates, of course, this 1000 volt per meter. So as I said, we applied the signal down here, and what's happening basically in time domain. So we have a voltage applied there, so we have a let's say mismatch of the charges between the top and bottom side, and the charges now start to propagate, and they start to flow around the conductors because charges can propagate on conductors, and that's how our signal propagation is happening. And now we can think about like Maxwell equations because this thing actually now they happen simultaneously. If the charge propagates, it's creating a current, and this is the current we see. The current propagation itself again is created an electric field, and the time derivative of the electric field is the curl of the magnetic field. So there is also a magnetic field around the signal trace. It's all probably you are well known of this kind of field distribution, but it's important to see that these things happen simultaneously. It's not like the one happens after the other. So we have a current, we have a magnetic field, and we have an electric field, and they are each of them has a certain extent, it has a certain distribution over the geometry, which of course depends on the signal trace and on the ground plane. So right now I have a pretty wide ground plane, so you have this kind of well-known distribution. If we would cut off the ground plane, we will also see more fringing fields around here. And because of the size of the fields, also what's of course important, like the current, it's also not bound. Of course, on a signal trace, it can only be, it's pretty much bound to the signal trace. But on the ground plane itself, you can see that has a certain distribution. If I rank up this, of course, it falls off, but it is still present on the signal trace. So there is I think, a very important step in trying to understand signal propagation, also thinking in terms of electromagnetic fields. And so we can now let the current propagate. So you can see this is our pulse. The signal trace length is pretty long, so when it arrives here at the point 2.5, it's basically the end of the signal, and you can see also now the end of the signal. So that's really a a true time domain description of the signal propagation and got some really interesting fields. For example, if we look at the electric field and I show it in terms of contours, we start at point 0 in time. Here's the pulse coming, and let me crack up the electric field a little bit to see also some smaller effects that I was talking about. So you can see the electric field, even if it's very small, you can see kind of like wave effects, like a wave propagation, and also some trailing fields which distribute all over our geometry. So it's never bound to just one position what's happening. It's always distributed over the complete geometry. Of course, that's a very small value. Think that there was 1000 volt per meter between the trace and the ground plane at the position of the signal trace. But nevertheless, the fields are there, and there are also other applications where even this kind of small fields can make problems. For example, in RF descents, where really small values on voltages can lead to system degradation. So keep this in mind, that it's the best always to think about fields and about Maxwell equation when looking at the propagation of signals on a PCB. I hope you have enjoyed this short lesson and have a further nice day. Bye bye.